All right, now we'll do another problem regarding this pressure prism as a way of solving, or as a alternative method of solving the hydrostatic forces. Okay, so for this problem, before that, for reference, this problem is taken from the same textbook that I've shown you in the previous videos. That's Introduction to Hydraulics by Cruz et al. Okay, so for this problem, it says a bulkhead 5 meter long divides a storage tank. One side of the tank is filled with oil of density 800 kilogram per meter cube to a depth of 2 meters, and the other side is filled with water to a depth of 1 meter, as shown in the figure. Determine the resultant force and its location. Okay, so the setup is that we have a storage tank, and in that storage tank, we have a divider, or a plate that divides the two fluids, and on one side of the tank is an oil with density of 800 kg per meter cube, and the depth is 2 meters. Then on the other side, there's a water, and the depth is 1 meter. So we are asked to find the resultant force acting on this divider. Okay, so for the solution, let's draw first the pressure profile. Okay, the pressure profile, or let's say 2D. Okay, and if we draw this, what we get is something like this. So since this is our object of concern, the center plate or the divider, then we have this pressure variation. So this one is water, and then this one is oil, and that just means that they have different slopes for this pressure profile. Okay, so let's label this as figure 1. Then if we also try to draw the prism, then we have this, and then another prism from the water, okay. So what is this pressure? We have to find this pressure, and what is this pressure? Okay, so let's say this is pressure A, and then this is pressure B, and we have a height for the oil side, that's 2 meter, and this one is 1 meter, and above, at this length right here, it says a bulkhead 5 meter long. So this one is 5 meters, and this one is 5 meters as well. Okay, so let's say this is figure number 2. Okay, so solve for PA and PB. So PA is just, right, so this is our A, this is our B, and let's say this is our point C and point D. Okay, so they're just 0. I mean, this C is 0 with respect to B, and this D is 0 with respect to A. Okay, so PA is just simply the unit weight of oil times the delta H. The unit weight of oil is 800 times G, 9.81, times the delta H of 2 meters. And that's 15 point, we can just write 15.7 kPa, kilopascals. And for PB, we have the unit weight of, okay, so for the PB, that's gonna be the side of the water, and this one is water times the delta H. So this is 9,810 Newton per meter cube times the change, times the depth, and that's just 1 meter. So it's 9,000 or 9.81 kPa. Okay, so now let's draw again. Okay, so drawing the profile again. We have this. Okay, so this one is P is equal to 15.7, and this one is P is equal to 9.81. This one P is equal to 0. Okay, so the centroid, if we also draw the centroid right here, that's going to be 1/3 from this space, and this one would be also 1/3 from this space, and that's where the force will act. Okay, so this is our F1, and this will be our F2. And the distance of F2, let's say this is our reference point, the bottom portion. That's our y sub 2, and then this one is our y sub 1. Okay, and the distance, that's just 2/3, right? So since this is 2 meters, then this one will be 2/3, and if this is 1 meter, then this will be 1/3. Okay, so number 4, solve for F1 and F2. Okay, so F1 is a triangular prism, so that's going to be 15 is equal to 15,000, let's say 700, that's in Newton per meter squared, right, times the height times 2, okay, divided by 2 because it's a triangle, times 5, and that's 78,500 Newton. Or I think we shouldn't have changed this because anyways, that doesn't matter. Okay, so for F2, then we have to solve what's the pressure. That's just 9.81, so 9,810 times the vertical distance, which is 1, and since it is a triangle, then you have to divide it by 2 times the length, and the answer is 24,525. That's in Newton. Okay, so next, solving for YCP. Okay, so, or I guess we have to solve for FD, the total force. So FD is just F1. Okay, so the force total is F1. That's not plus because they are acting in opposite direction. So if this is positive, this one would be negative. Okay, so that just means that we have an F1 minus F2. So that depends upon which you think, or I mean, in this case, we assume that the direction to the right is the positive one, and the direction to the left is the negative one. Okay, so F1 minus F2, therefore, let's see, 78.5 kN minus 24.5 kN. that's just 54 kN, kilonewtons. Okay, and therefore the YCP is just simply FP times YCP is equal to F1 times the Y1, right, minus F2 times the Y2. Okay, so if you solve this, what you get is YCP. YCP is equal to 0.82 meters from the bottom. Okay, so in summary, if we provide a summary for our solutions, then if this is our divider, and then this is our pressure profile for oil, and then this is our pressure profile for the water, then our location of the resultant force is somewhere here. That's 0.82 meters. Okay, and this will be the direction of our FR, which is 54 km. Okay, so again, if we do a recap on what we did, we first draw the profile because we want to visualize, and we solve for the pressure at this point, because that's going to be the axis for solving the prism, the volume of the prism. Okay, so we solve for the pressure, and then we solve for once we obtain this pressure, and since we have the height and the other lengths, the orthogonal lengths, then we can solve for the F1 and F2. And once we solve for the F1 and F2, then we can solve for the total force. And once we have the total force, then we can apply this equation to solve for the location of the center of pressure. Okay, and after that, please provide a summary in your homework. Okay, so the next thing that we'll do is to have another problem. Okay, so problem number 6, we have a pressurized cylindrical tank. So this one, it is pressurized. Most of the problems that we did, or I think all of the problem that we did, were open tanks, or tanks that, or containers, or situations where there's a free surface and the free surface is exposed to the atmospheric pressure. Okay, so for this one, it is a pressurized cylindrical tank, 0.8 meters in diameter and a total height of 1.8. That contains oil with an SG of 0.85 to a depth of 1.5 meters. The air pressure above the oil is 40 kPa. A viewing window is installed at the middle portion as shown. Determine the magnitude of the resultant force and its location that's acting on the viewing window. Okay, so basically what we have is something like this. And at the middle portion we have a viewing window. Okay, so the diameter is 0.8 meters, and we have an air gap of, that's 0.2 meters, and then from this to here, that's 1.6 meters. So we have a total height of 1.8 meters. Now this viewing window, it's 0.2 by 0.2 meters, and the location of this one from, let's say, from this layer, this surface, that's 0.7 meters. Okay, so the half is 0.9, so 0.9 minus 0.2, that's 0.7 meters. Okay, so for that solution, again, we just have to sketch the pressure profile. Okay, so if we sketch the pressure profile, we have this section, and this, let's say this is oil, and this is our viewing window. Okay, so the pressure profile would be something like this. Okay, so this is not zero because there's a reading. There's a reading of pressure. It's actually pressurized, and it's given that we have a reading of 40 kPa. Okay, so in other words, there's a pressure from the air, and it's producing a pressure of 40 kPa. Okay, so if this is our zero pressure line, then it should be 40. Okay, so let's say somewhere here, there's gonna be somewhere here. Okay, so this is 40 kPa. Then from this surface, we can apply the hydrostatic equation, and we can see that the pressure variation would be something like this. Okay, so this is 40. However, what we only need is the pressure along this window, right? So this is our pressure. Yeah, therefore, we need to solve for the pressure here. Okay, so we have this one, we have the pressure there in this point, but we need the pressure right here and the pressure at this point. So let's say this is pressure B, or our point B, and this one would be our point C. Okay, so that's right, this is our figure 1. And for figure 2, if we try to zoom out, or I mean zoom in, then that's gonna be okay, so this one is this pressure line. This is the zero pressure line, and this pressure right here at this point would be P is equal to 40 kPa. And then at this point, this is what we don't know, and this is P sub P, and this one would be P sub C. And let's label this figure as figure number 2. Okay, so the next step is let's say referring to figure number 2, the pressure B at B and C will be calculated first. Okay, so PB is just simply PA. That's right here. This is our B, this is our C, and this is our A. Okay, so PB is equal to PA plus the this one, delta H. Okay, so our PA is 40. Okay, that's in kPa, and this one would be plus 9.81 times the specific gravity of the oil, 0.85, times the distance. Okay, so from this surface up to the centroid of this viewing window, that's 0.7, and this is 0.2, so 0.7 minus half of 0.2, and it's going to be 0.6 meters. Okay, times 0.6 meters. Okay, so if we do the math, what we get is 42.9 kPa, and PC is equal to PB plus this one. So PB is 42.9 plus, okay, this okay, so from this point to this, that's our P sub C. So 42.9 plus 9.81 times 0.85 times 0.2 meters. Okay, the question is, why is it 0.2? It's simply because we are only evaluating the pressure from point B to point C. So that's why that's 0.2. Earlier, when we solved for the pressure at B, we are evaluating the pressure from point B to point A. And this is our point A. This is our A, this is our B, and this is our C. Okay, so if we do the math here, we have a value, or we'll get a value of 44.6 kPa. And what we want is PB, or PC minus PB, which is just equal to 1.7. Okay, so 1.7 kPa. Okay, so now that's okay, step number 3. Okay, so sketch the results, and that's going to be right. This is our B, this is our C, and this is our viewing window. Therefore, we can have I mean, since we have a trapezoidal prism, then we can divide it into a rectangular and a triangular prism. Okay, so for this portion, let's say this is our point 1, then this is our point 2. For the rectangular, the centroid is somewhere right here, and the centroid is 1/3 from the base. Okay, so that's where the force will act. Okay, so this one is F sub 2, and then this one will be F sub 1. And the distance, and let's say this is our reference point, the bottom, then this will be 1/3 of 0.2, which is just equal to 0.13 meters. And this one, that's just 0.1 meters. Okay, so for the pressure axis, this is PC minus PB, which is 1.7 kPa, and this one is 42.9 kPa. Okay, so solving number 3, number 4. Okay, so solving now for the forces. Okay, so for F1, we just have, okay, this is our F1, our rectangular prism, which is 42.9 kPa times the height, which is 0.2 meters. Okay, let's write the units, times the orthogonal length, which is also equal to 0.2 meters. And what we have is 1.716 kilonewtons. Now for the force at prism number 2, we have 1.7. Okay, so that's the triangular portion, 1.7 kPa times the height is 0.2 divided by 2, because that's a triangle. Then we need to multiply that to the orthogonal length times 0.2 meters. And what we get is 0.035. 4 meters. And therefore, FR, the total resultant force, is simply F1 plus F2. It is plus because they act towards the same direction. Okay, so we have 1.716 plus 0.034. We get a value of 1.75 kilonewtons. Therefore, to solve for solving now for YCP. Okay, and YCP is just equal to F1 Y1 plus F2 Y2 divided by the total force. Okay, so again, this equation just says that the total force multiplied to the location, or let's say to the moment arm, is just equal to the sum of the product of the force and their, or the individual forces and their moment arms. Okay, so if you substitute all the values, what you get is let's say 1.716 times 0.1 plus 0.034 times 0.13, then 1.75 divided by 1.75, and you get is approximately 0.1 meters. Okay, so lastly, for the summary, okay, so this is our tank, and then this is our viewing window, and this is our level of water. Okay, that's not right, this symbol. And since this is at this pressure right here, at 40 pressure, then this will be the pressure profile acting on the window, and the force be somewhere like, all right, so this is our FR, and then this will be our 0.1. Okay, so it's actually approximately 0.1, but it's probably because we only have a slight variation or small values of forces here. Okay, so again, if we do the recap, this is our problem. This is a pressurized system, and even though it's pressurized, we can still apply the volume of the the method of using the pressure prisms. Okay, so this our problem is a cylindrical tank, and we are to solve the viewing window. We first establish the values of the pressure at the points. Then once we have the pressure at the points, then we can solve for the forces. Once we have the pressure at the points, then we can actually dimension the prism, okay, because the pressure is the x-axis. Okay, and once we have all that, we can solve for the volume, and that corresponds to the forces. And once we have the forces F1, F2, then we can solve for the resultant force. And once we have the resultant force, then you can solve for this location of the resultant force. Okay, so just to give you a heads up, in your homework, you'll be asked to solve for the same problem, except that we don't have this viewing window, and you are asked to solve for the pressure acting on the wall. Okay, so if that's the case, even though this is a cylinder, right, and let's say we have this pressure variation, let's say it is still pressurized, so we can have a profile something like this. Okay, so let me draw it again here. This is our profile, and since it is pressurized, then on this level, that's 40 kPa, for example, and we have this pressure variation. Okay, so to solve for this, you have to also, again, the same procedure that we did. You have to solve for this. Let's say this is our PB, and then this is our P sub C. Then you can, or you should divide it into these two prisms. Okay. Okay, so let's say this is our prism 1, and then this will be our prism 2. Okay, so it doesn't matter now, let's say, even though this layer is a layer of air, and then this bottom layer is a layer of oil, even though they have different densities or specific weights, what we're solving right here is the pressure. So at this point we have a pressure of 40, and therefore in this prism, what you'll use is the pressure at 40. Okay, and then here you have to use the pressure in, I mean, the pressure difference, okay, from whatever value that you get in this point. Okay, so it's all about geometry, and that's why we say it's a geometric method. Okay, so if you are asked to find this, then how do we use the prism if this is a cylinder? Then of course, if this is a cylinder, then you can just imagine that you cut this portion right here, and then you lay it out in flat. Okay, so it's like, what you get is something like this. Okay, so it's a cylinder. However, if you cut it here, so you lay it out in a flat position, so what you get is also a plane, a rectangular plane. Okay, and then this will be our pi d. That's the circumference of this cylinder. So pi d, and then this one is, let's say, the height. So if you have the air, let's say we have the air layer, and then we have the oil, so you have this height right here. Okay, so enough with this. In the next videos, we'll be starting a new topic, which is the relative equilibrium, or what will happen if a static fluid that's inside a container, but this container is accelerating, or it's in motion. Okay, so what will happen to the hydrostatic equations? Okay, we will skip for now the topic on forces on curved surface. Okay, so that's all, and see you in the next video.